Welcome to this problem on projectile motion, where a golfer hits a golf ball and we determine how far the ball goes, how high the ball goes, and the impact velocity of the ball. A golfer hits a golf ball with an initial velocity of 45 meters per second at an angle of 35 degrees above the horizontal. In part A, we'll find how far from the golfer the ball lands. In part B, the maximum height reached by the ball, and in part C, what will be the ball's impact velocity. Before we start part A, we'll make a diagram on the right and list our variables. So the golfer hits the ball with an initial velocity of 45 meters per second at 35 degrees above the horizontal. So let's add this to the diagram. Our VI is equal to 45 meters per second, and our angle here is equal to 35 degrees. In part A, we're asked how far from the golfer does the ball land, and that's our horizontal displacement here. So we can add that to the diagram. That's our D in the X direction. In part B, we're asked the maximum height reached by the ball, so that's our displacement in the Y direction. So we can add that to our diagram as well, right here. So that's the maximum height reached in the Y direction. So that's our displacement Y. And now we're ready to list our variables. We'll break them up into the X variables and the Y variables so we stay organized throughout the question. In the X or horizontal direction, we have no acceleration the moment the ball leaves the club face. So because we have no acceleration, we can just use our equations of motion. So the only variables we have in the X direction are our velocity, our displacement, and our time. In the Y direction or the vertical direction, we have the acceleration of gravity. So we'll have to use our kinematic equations. So that means the variables we have in the Y direction will be our velocity initial, our velocity final, our displacement, our acceleration, and our time. Right now, our initial velocity is at an angle of 35 degrees, so we have to break this into the X and Y components so we have the respective velocities. To find these components, let's just blow this up into a little bit bigger of a diagram. We break this vector into its respective component in the Y or vertical direction, and its respective component in the X or horizontal direction. Using our 35-degree angle here, we can now calculate the Y and X components. We do this using trigonometry, so we can call this side here Vy and this side Vx. To solve for the side Vy, or our vertical velocity, we have the opposite side and we have the hypotenuse. So we can use sine. Sine of the angle is equal to opposite over hypotenuse. Adding in our numbers, we have sine of 35 degrees is equal to Vy, the side we're searching for, over 45. Vy is being divided by 45. So to get Vy all alone, we multiply both sides by 45. On this side, 45 divided by 45 is equal to 1. So we have Vy all alone. On this side now, we have 45 multiplied by sine of 35. This gives us 25.81 meters per second. And this is equal to our velocity initial in the Y direction, Vy. We can add this up here. Vi, or our velocity initial in the Y direction, is 25.81 meters per second. And we'll keep an extra decimal place just to avoid rounding errors. Now we're ready to find Vx. Vx is the adjacent side. So we have the angle of the adjacent side and the hypotenuse. So we use cosine. Cosine of the angle is equal to the adjacent side divided by the hypotenuse. Bringing in the numbers, we have cosine of 35 degrees is equal to, our adjacent side is our Vx that we're looking for, divided by our hypotenuse, which is 45. Again, we solve for Vx by multiplying both sides by 45. On this side, our 45 and our 45 equal 1, so we're left with just Vx. And on this side, we have 45 multiplied by cos of 35, and we get 36.86 meters per second. This is our velocity in the x direction. So we can add that up here, 36.86 meters per second. And again, we keep an extra decimal place to avoid rounding errors. We're now ready to start solving. So the question is, how far from the golfer does the ball land? So we're looking for our displacement here in the x direction. That's this, our displacement in the x. We can't solve for it directly because we also don't have the time. So we know we're going to have to find time first here in our y component. In the y direction, we have our initial velocity, which is 25.81 meters per second. We also know that our acceleration due to gravity is equal to negative 9.81 meters per second squared. And it's negative because it goes in the downwards direction. What we're looking for is the time, and we don't have it. We also don't have the displacement in the y direction. So we need our VF if we want to start solving. So we have to be a little bit crafty with how we set up this problem. One thing we do know is that VF is equal to 0 at the very top of the flight of the ball. If you think about a ball traveling upwards, it slows down, it slows down, it slows down, it slows down. At the very top, although it's still moving sideways in the x direction, the ball is neither moving up nor down. So we cheat this problem in a way by finding only half the time. We find the time it takes the ball to reach the top. After that, we know that the two sides are symmetrical and we can just double it. So our VF at the very top is equal to 0 meters per second. And let's just mention it's at the top in our variables so we don't forget and use it later on. Now that we have three values, we're ready to pick our kinematic equation. We're not looking for it, and we don't have the value for the displacement d. So we can cross out all the equations that have displacement in them. This leaves us with this equation down here. So velocity final is equal to the velocity initial plus the acceleration multiplied by the time. We add in our values. Our VF is equal to 0 meters per second at the top, so 0 here is equal to our VI of 25.81 meters per second plus our acceleration of negative 9.81 meters per second squared multiplied our time. To start solving this, we're looking to get our value with our t all alone, so we have to move out this term here. So we minus 25.81 meters per second from both sides of the equation. And on this side here, 25.81 subtract 25.81 is just 0. And on this side, 0 minus 25.81 is equal to negative 25.81 meters per second. And this is equal to this term 0. So all we're left here is our negative 9.81 meters per second squared multiplied by our t. The negative 9.81 is multiplying the t, so to get t all alone, we have to apply the opposite of multiplication, which is division. So we divide both sides by negative 9.81 meters per second squared. Negative 9.81 meters per second squared. So on this side, the negative 9.81 divided by the negative 9.81 equals 1. So we're just left with t. And on this side, negative 25.81 divided by negative 9.81 equals 2.630 seconds, and we'll keep an extra decimal point here to avoid some rounding errors. Now the key to remember is that we set VF equal to 0 meters per second at the top to solve this problem. So the time we actually found was the time it took for the ball to rise to the top after being struck. We didn't calculate how long it takes to get back down, but since it's a parabola, it's symmetrical. The amount of time it takes to the top is the same amount of time it'll take to drop back down to the bottom. So we can simply multiply this time by 2 to get the total time of flight. So 2.630 seconds multiplied by 2 is equal to 5.260 seconds. We can now add our time value to our list of variables. So 5 5.260 seconds. Now, time is the only value that can actually be used on both sides. So the time in the x direction is the same, 5.260 seconds. This is because time is a scalar value. It has no direction, and we broke these two sets of variables up by their direction, but time has no direction. You'll notice everything else here has direction on it. We now have the two variables we need in the x components to solve for dx, how far from the golfer the golf ball lands. There is no acceleration in the x direction, so we don't have to use a kinematic equation. We can just use our equation of motion. V, velocity, is equal to the displacement over the time. Adding in our values, for v we have 36.86 meters per second, and this is equal to our displacement, which is what we're looking for, divided by our time, which is 5.260 seconds. 5.260 seconds. Our displacement d is divided by 5.260 seconds, so to get d all alone, we have to do the opposite. So we multiply both sides by 5.260 seconds, multiply by 5.260 seconds. So on this side, 5.260 seconds divided by 5.260 seconds just equals 1, leaving us with our value of d. And on this side, 36.86 multiplied by 5.260 seconds equals 194 meters. This is our displacement dx in the x direction. So how far from the golfer does the ball land? It lands 194 meters from the golfer, our value here of dx. We can add it to our variables just so we have it. So 194 meters. And now we're ready to move to part B. Part B asks, what is the maximum height reached by the ball? This is our dy term here, and we can really just leave the setup the same. Our initial velocity in the y direction is still 25.81. For this problem, we can again use Vf is equal to 0 at the top, because when the ball reaches its max height, it will be at a velocity of 0 because it will no longer be moving up or down. Gravity is still negative 9.81 meters per second squared. And if we wanted to use our time, we'd actually have to be careful here because the ball reaches its max height at half time, not full time. But since time is a calculated value, we're not going to use it here anyway, just in case we made a mistake when we calculated it. So we're ready to pick our kinematic equation. Since we're not looking for the time, and we're also trying not to use it, we can just cross out all our kinematic equations that have time in them. So that leaves us with this equation here. Let's just double check. Yep, this one also has time. So if we write this up here, Vf squared is equal to Vi squared plus 2 multiplied by the acceleration multiplied by the displacement. Bringing in the numbers, we have a Vf value of 0, so 0 squared is still 0. And this is equal to our Vi squared, which is 25.81 meters per second. And this is squared plus 2 times multiplied by the acceleration, which is negative 9.81 meters per second squared multiplied by our displacement, which is what we're looking for. 25.81 squared is equal to 666.2 meters squared per second squared. And we add this to our 2 multiplied by negative 9.81, which is negative 19.62 meters per second squared multiplied by our displacement. And this is equal to 0. To get our term with the displacement all alone, we start by subtracting 666.2 from both sides, minus 666.2. So on this side, 666.2 minus 666.2 is just 0, and on this side, 0 minus 666.2 is negative 666.2 meters squared per second squared. And this is equal to our term up here of negative 19.62 meters per second squared multiplied by our displacement. Negative 19.62 is multiplying the displacement. So to get the displacement all alone, we have to apply the opposite. So we divide both sides by 19.62 meters per second squared, divided by 19.62 meters per second squared. So on this side, this division just equals 1, leaving us with our displacement d equal to negative 666.2 divided by negative 19.62 equals 34.0 meters. So the maximum height reached by the ball, our displacement in the y direction, is equal to 34.0 meters. We can add this to our variables here. We're now ready to look at part C. In part C, we're asked what will be the ball's impact velocity. This question can be solved two ways, and one is with reasoning and one is with math. With math, we would have to set up the problem slightly differently, but we'd solve it sort of the same way. So we would solve the back half of the arc. So our VI would actually be our 0 at the top, and we would find our VF at the bottom. So that would be our VF in the y direction and our VF in the x direction. And we could do this using our times and the other variables now that we have the height it's falling from and gravity. This is a lot of math. So a quicker way to find the impact velocity is to reason through the question. Because we have a parabola here, we know that the impact angle here is also 35 degrees. And our impact vector is coming in at 35 degrees. Blowing this here up a little bit right here, we have our impact vector, and we'll draw the horizontal above our impact vector. And we have our angle of impact of 35 degrees. This light blue line is just an aid to describe impact velocity. It's sort of a fictitious line that floats here above our vector. The angle we're actually looking for to describe our impact velocity is this angle right here. And this angle is also 35 degrees because if two parallel lines are intersected by a line, then the inside angles are also the same. Due to the symmetry of the problem, our VF final is the same as our VI initial. This is not in the X or the Y. This is our total component. So just like our initial launch velocity here was 45 meters per second, our impact velocity here, we'll call it our VF, is equal to 45 as well. If you're not quite convinced, remember that all the velocity that's lost by the ball on the way up, which is our Vy component here, is gained by the ball as it falls back down to the ground. Our Vy on the way down is equal to on the way up, but in the opposite direction. Our Vx stays exactly the same. The x velocity of the ball never changes from the moment it leaves the golf club. Due to this, our triangle stays the same except for our Vy vector flipping, which means our hypotenuse or our impact velocity will also stay the same in magnitude. The direction will change to downwards. So what will be the ball's impact velocity? It'll be 45.0 meters per second at 35 degrees below the horizontal. We say below the horizontal because if you were to continue this vector through the plane here, this would be your 35 degree angle here, and this angle is below the horizontal. It's just easier to add a hypothetical line up slightly above the impact vector to show our below the horizontal. So our 35 degrees below the horizontal. This should make sense with our initial launch velocity being 35 degrees above the horizontal. Thank you for watching this video on projectile motion, where we found the maximum distance a golfer would hit the ball, the maximum height the ball would reach, and the impact velocity of the ball.